Okay, in this video we're going to be looking at the derivation of the formula d sine theta is equal to m lambda. Okay, so consider this. We have our double slit experiment here. We've got a single slit, double slits going to a screen. We're going to have a slit separation here of lowercase d. We're going to have a point here which is going to be point capital M. This is the midpoint of the two slits. Directly opposite that on the screen, I drew a dotted line. No decent dotted lines. Oh, that one will do. Go from there to there. And I change it slightly because I don't like the look of it. Okay, so if I travel from M directly opposite onto the screen there, I'm going to have a point that I'm going to call P0. So that's our central maximum. So if I then have another first order maximum somewhere out here, or a second order, or just a maximum somewhere, and I draw a line from here to here, where my P0 is, from my P0 up, I'm going to get a point P where my maxima is, and I'll get rid of this extra bits in the lines. I then have something that looks like this. This forms an angle, as you can see, and it's a right angle triangle. So this angle in here, we're going to call theta. So midpoint to directly opposite that, we get the central band, and then we get a maxima somewhere up here. So the light coming from the two slits to point P will look something like this. So I'll have one wave of light reaching up there like that, and the one down here travels from there to there. I'm going to change the colour of them to make it easy to see. So the top one's going to be red, bottom one is going to be green. No, not green, because everything else is green. Make it light blue. So we have this. I'm going to call the top wave S1, and I'm going to call the bottom wave S2. Now, if I draw a line between these two waves, which, if I draw this line, the distance from here to here, and the distance from that point, which I'm going to call point D, to that point P, is going to be the same. So it goes something like that. This angle here is also theta, so it's the same angle as what forms here. Just some good mathematics that ends up doing that. So, from this diagram we can see something. Our path difference, we're going to call delta S, is going to be equal to S1 to P, and so that's the first wave, and the second wave S2 to P. The path difference of those two P's is going to be S2 to D. So I can write that up. The absolute value of S2 to P, take away S1 to P, going to be equal to S2 to D. So our path difference is this. Now I'm going to take this triangle we have here, and I'm going to draw it here. So it will look something like this. And not quite like that. I need it bigger, sorry. Okay, this side here is going to have a length of d, lowercase d, so the slit separation. We know that because it's this side here. This bottom side here is going to have the length of S2d. So this is S2d. Our angle up here is theta. And this top side is S1 to d, because it's from here to here. Okay. We can approximate this angle down here to 90 degrees. It's going to be very close to 90 degrees, so we can just approximate it to 90 degrees. Now, if I take the sine of this, so the sine theta is equal to opposite over hypotenuse. If I take the sine of this, I end up with sine theta is equal to opposite side, which is S2d, divided by lowercase d. If I rearrange this now, I'm going to get, and I want to get this by itself and the d away from this side, I'm going to get d times by sine theta is equal to my path difference of S2d. Now, my S2d is my path difference, so I can write d times by sine theta is equal to delta S. If my point P is a maxima, the path difference has to be equal to m lambda, where m is some integer. So, we can rewrite this as d sine theta is equal to m lambda, where m is some integer. This has to be where there's a maximum. If I have a minimum, my path difference is going to be m plus a half lambda. But you need to know how to do this. So that's how we derive the formula. D sine theta is equal to m lambda. We use simple trigonometry.